Here we have two probability experiments. The first probability experiment is a theoretical probability, and the second probability experiment is an empirical probability. So this first one is rolling two dice and recording the value on each die. Now notice I've already represented the sample space over here. This is not a tree diagram, but it's a perfectly good representation of the entire sample space. For example, you have 1 with 1, 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6, 2 with 1, 2 with 2, 2 with 3, 2 with 4, so on and so forth, all the way through. So our first question is, what is the sample size? Well, if you notice, this is a 6 by 6 rectangle, 6 rows, and 6 columns. So 6 times 6 gives us a total of 36 outcomes in the sample space. So the sample size is 36. We'll pay attention to that multiplication we just did in a little bit. Now, what's the likelihood of rolling doubles? Well, we go through and find the event space. In this case, the event space is for rolling doubles. So we'll go through and you can see all the doubles are along the diagonal here. So the event space has size 6. There's 6 doubles there. So our probability, our likelihood, is 6 out of 36. Of course, you could reduce that to 1/6 if you'd like. You could put it in a decimal, you could put it in percentage form, doesn't matter. Finally, what's the likelihood of not rolling doubles? Well, technically, you could go through and count all the rest of these. All the rest of these here and here. All of those are not doubles. But that's a waste of time. We've already discussed that when you have complementary events, and here we do, rolling doubles is complementary to not rolling doubles, we can compute the likelihood of the complementary event by doing 1 minus the complementary event of rolling doubles, which is 636. So 1 minus 636 is equal to 3036, which of course can be reduced to 56. Again, you could have gone through and added all these up and get 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. You would get a total of 30 of them, and then your probability would be 30 out of 36, but that's a waste of time. Using the relationship between complementary events is much quicker and more efficient. Let's now look at the second probability experiment. In this case, you have the results of a survey on cheese preference below. So 43 people surveyed preferred cheddar the most, and 17 preferred Swiss, 9 preferred provolone, and 32 preferred mozzarella. So what's the sample size here? In this case, our probabilities are built off of data from a survey, so this will be an empirical probability. And how many people did they talk to? Well, if you add these up, you get a total, which of course is represented by sigma f, you get a total of 101. So they surveyed 101 people. So the sample size is 101. There's 101 data points. If chosen at random, what's the chance a person prefers Swiss? Well, there are 17 people who preferred Swiss out of the 101. So you have a 17 in 101 chance. Again, you could write this as a decimal or a percentage if you'd like, or leave it as a fraction. If chosen at random, what's the chance a person does not prefer Swiss? So that means anything else. Technically, you could go up, add up the cheddar, the provolone, and the mozzarella, but that's a waste of time. If 17 preferred Swiss, the rest of them do not prefer Swiss. There's a total of 84 left. 84 out of 101. Remember, complementary events, their probabilities add together to 1. Now that we've looked at a theoretical and an empirical example, let's now connect the theoretical and empirical. And the connection between those two is called the law of large numbers. Well, for example, that survey could not be done theoretically. That's purely done empirically. You could technically do the rolling of two dice empirically. You could roll a set of dice 100 times and record each time what the result is. And then however many times you got doubles, you'd probably say that's the amount of time out of 100 that you would get doubles. That would be an empirical approach to that problem. But for problems that can be looked at empirically and theoretically, there must be some sort of connection between the two. And again, that is what we call the law of large numbers. So here you can see an experiment that I've already done. If you were to go to this website, you could do it yourself. It has a coin flipping simulator. And basically what I did is I had the simulator flip a coin 10 times, and it recorded the number of heads. And I got 6 out of 10, which of course is 60%. And I'll get over to this one in a minute. So 10 flips, 6 times it came up head and gave you a percent heads of 60%. Is that what you expected? What do you think the most likely percentage is that you would get? Probably you would say 5 out of 10 because you expect 50% heads, 50% tails, but it doesn't always come out exactly like that. You could very well get 6 heads out of 10 flips. It would be hard to get 10 heads out of 10 flips, but 6 or 4 out of 10 is not extreme in any way. So what if we kept doing this? I had the simulator flip a coin 100 times, 1,000 times, and 10,000 times. When I flipped it 100 times, or the computer, I should say, flipped the coin 100 times, there were 51 heads, giving us a 51% heads. When it flipped 1,000 times, there were 484 heads, which is 48.4% of the time. And then when it was done 10,000 times, it had 4,943 heads, which gives you 49.43% heads. Now, the law of large numbers basically says as these numbers get bigger, the more times you do an experiment, the empirical probability approaches the theoretical probability in the long run. So as you do an experiment more and more times, your probabilities should approach the theoretical probability. Again, the theoretical probability here is because there's a 50-50 chance of getting a heads or tails, the theoretical probability is 50%. So what this last column is shows you how far off these are. So if you did 60% minus the 50%, 51 minus the 50, 48.4 minus the 50, and 49.43 minus the 50%. Notice this first one's pretty far off, 10%. Then this one's only off by 1%. This one's off by a little bit more, but it's not too bad. And then this is getting even closer. It's only 0.57% off below the expected amount. If you kept doing this, say I do it 100,000 times, 1,000,000 times, this number right here would get closer and closer and closer to 0. That would mean that the empirical probabilities are getting closer and closer and closer to the theoretical probabilities. This is what we call the law of large numbers. Again, going back to the problem of rolling 2 dice and recording the results, we want to look at exactly the size of the sample space. If you can recall, there was a 6 by 6 rectangle that gave us a sample space of size 36. This is a specific example of an extremely important counting principle known as the fundamental counting principle. It says that if task 1 can be done in m different ways and task 2 can be done in n different ways, then the 2 tasks can be done in sequence in m times n different ways. And this is generalizable to any finitely many tasks. So what this means is the sample size could have been computed without even having that graphic. For when you roll 2 die, you have, let's say you've got, or 2 dice, you've got die 1 and you've got die 2. Well, on die 1, there's 6 different possibilities. That's task 1. And then task 2, there's 6 different possibilities, which is rolling die 2. So if you're going to do both of them in sequence, i.e. you're going to roll both of the dice, then you can take the product of those two to get the total number. And 6 times 6 gives you 36 total outcomes. This is a quick and easy way to find the size of the sample space. In fact, that number right there is so important, it showed up as the denominator in each of the probabilities in that particular problem. Let's try another problem like this. In this next example, suppose you have motorcycle license plates in Wyoming consisting of 5 characters and have the following scheme. The first, second, and last characters must be letters. The third and fourth characters must be digits. The digits can repeat, but the letters cannot. So let's suppose this is their scheme. Again, you've got 5 characters on the license plate. The first, second, and last characters must be letters. And don't forget, we've got 26 letters in our alphabet. And the third and fourth spots are digits. And don't forget, we have 10 digits in our number system. But notice here, it says the digits can repeat, but the letters cannot. So how many license plates are possible? So the first, second, and fifth spots are letters, but the letters cannot repeat. So that means for the first spot, you've got a choice of 26 letters. But whichever letter is used, you then have one less. You can't use that same one in the next spot. That means there's only 25 left. And then once you've used these two, then there's only 24 letters left to go in the last spot. Any of 24 to choose from, that is. And then the digits can repeat, but the letters cannot. So you can put any of 10 digits here, and any of the 10 digits here. And by the fundamental counting principle, if we take the product of these 5 individual tasks, you get a total of 1,560,000. This is how many license plates are possible. Now that we know all of the possibilities, we can now answer a probability question. What's the likelihood Steve will get the license plate NJ33P if he's assigned one at random? Assume none have been given out yet. So NJ33P is one specific license plate that fits this condition. Well, that's one out of this total of 1,560,000. So there's a 1 in 1,560,000 chance that he will randomly be assigned that license plate. So it is highly unlikely that he will be assigned this license plate. That's the reason we have vanity license plates. If you really want a particular license plate, you can pay extra money to get it.